All right, so now let's talk about the pH scale, because really when we talk about acidic and basic solutions, what you hear a lot is a pH value. If we go back to some of these examples that we did, we see that over and over and over again, we're getting concentrations that are like 10 to the negative something, 10 to the negative something, 10 to the negative something, right? Scientists don't really like to work in numbers like that in scientific notation. And it turns out that typically the pH, the concentration of hydronium ions in a solution will range from 10 to the negative 1 to 10 to the negative 14. That's a typical range of concentration of hydronium ions for a solution. Again, you're always seeing that 10 to the negative, 10 to the negative. Well, scientists don't really like using that. So instead they use what's called a pH scale, where you take that concentration of hydronium ions and you take the negative log of that concentration. Okay, so first of all, what I want you to realize is that pH is directly linked to the concentration of the hydronium ions. If you know the pH, you know the concentration of hydronium ions. And if you know the concentration of hydronium ions, you know the pH. They are the same pieces of information, just like formatted a little bit differently. Okay, so step one, first thing I want you to have just ingrained in your brain is this: if I know pH, I know hydronium ions. If I know hydronium ions, I know pH. They're one and the same, right? They're the same piece of information. But it's just a log of that hydronium ion. So just to remind everybody, like the log of 10 to the A is that exponent A. Right, that's what a log is doing for you. Okay, so the pH is, I'm going to take the negative log of the concentration of the hydronium ions, and that would be my pH. Similarly, there's this concept of pOH, which is the log of the hydroxide ions. So if you're given the concentration of hydronium ions or hydroxide ions, you can use this formula to find the pH or the pOH. Okay. How do I go the reverse direction? Taking 10 to the negative of whatever the pH is will give you the hydronium ion concentration. Likewise, taking 10 to the negative pOH will give you the concentration of the hydroxide ions. Okay, that's like the reverse, the inverse process. And then lastly, our expression for Kw, if we look at it in log form, is that the pH plus the pOH will always equal 14. Okay, so pH plus pOH equals 14. All right, so I told you that a typical concentration of hydronium ion range is 10 to the negative 1 to 10 to the negative 14. That means that the pH range is typically between 1 and 14. Okay, we've also said that H3O plus concentration equal to 1 times 10 to the negative 7. This would be considered neutral. This corresponds to a pH of 7. If I took the negative log of 1 times 10 to the negative 7, it would be 7. So a pH of 7 is considered neutral. Anything less than that is acidic. Anything more than that is basic. All right. The other thing about these pH calculations that are going to be kind of a pain in the butt is the Sig Fig rules. All right, so the rules for carrying significant figures with that log function are different than any of the rules that we've studied thus far. Okay, so we've studied rules for addition and subtraction. We studied rules for multiplication and division. Those were two separate sets of rules. Now we have a third set of rules for those log functions. So what we're going to find is these significant digits in the number of significant digits in the concentration of hydronium ion is going to equal the number of decimal places in the pH, right? So let's look at these examples here. Here, 1.00 times 10 to the negative 12. I have 3 sig figs in this measurement, right? 3 significant digits. That means I should have 3 decimal places on my pH. So I'm not looking at sig figs in the pH, I'm looking at decimal places, right? Sig figs in hydronium ion concentration refer to decimal places in my pH. That's how we carry sig figs for a log function. Yeah, so you could just sort of convince yourself of these examples. If I had 9 times 10, 9.0 times 10 to the negative 8, that would be 2 decimal places. So when I take the negative log of that, I punch that into my calculator, I get 7.05, right? So negative log of 9.0 times 10 to the negative 8. I punch that into my calculator, and then I'm going to report to 2 decimal places because I had 2 sig figs in my starting measurement. All right, so that's how we carry sig figs for our pH and our pOH calculations. All right, so let's do some examples. Determine a pH of a solution where at 25 degrees Celsius, where the hydronium ion concentration is 3.5 times 10 to the negative 4. So everybody make sure that we can do this in our calculators. We're going to take the negative log, so find that log button, and you're going to punch in the 3.5 times 10 to the negative 4. You're going to take that log, so 3.5 times 10 to the negative 4. Take the negative log of that, and you get 3.45593. How many sig figs, or how many decimal places should I have in my pH? Remember, I want as many decimal places as I have sig figs. So this is 2 sig figs, which means I'm going to need 2 decimal places. So my pH is equal to 3.46. pHs don't have units. Okay, so you actually don't have any units associated with that. For example B, I'm going to take the negative log of 1.7 times 10 to the negative 7, punch that into my calculator, and I get 6.76955. I have 2 sig figs in my concentration of hydronium ion measurement, which means that I should have 2 decimal places in my pH. So this would be a pH equal to 6.77. All right, last example, I'm going to take the negative log of 8.80 times 10 to the negative 11. Punch that into my calculator, and I get 10.055551. In this example, or in this problem, I have 3 sig figs in my hydronium ion concentration, which means I'm going to need to round to 3 decimal places. So this would be 10 pH equal to 10.056. Right, notice the difference in sig figs in B versus C is what led to a different number of decimal places in B versus C. Okay, the other thing I want to point out is that you can always kind of like check to make sure your calculations are reasonable, because the exponent is pretty close in value to the pH that you get. It's always within 1 unit. So my exponent of negative 4, I had a pH of 3. My exponent of negative 7, I have a pH of 6. Exponent of negative 11, I have a pH of 10. So always within 1 unit of that exponent. So it's just an easy way to make sure that you haven't messed up in your calculation. Okay. Now we're going to go the other direction. So what's the concentration of hydronium ion solutions? What's the concentration of hydronium ions in a solution with the following pH? So concentration of hydronium ions is equal to 10 to the negative pH. So you're going to take this value and raise 10 to the negative 4.76. Punch that into your calculator. 1.7378 times 10 to the negative 5. And again, how do we do sig figs for this problem? It's the reverse of what we just talked about. Here I have 2 decimal places, which means that I should have 2 sig figs in my final answer. So the concentration of hydronium, should put the positive there, for this example is 1.7 times 10 to the negative 5 molar, right? Our concentrations are always in molar. 11.9500. I'm going to take my concentration of hydronium ions is equal to 10 to the negative 11.9500. Punch that into my calculator. I get 1.12202, 1.12202 times 10 to the negative 12, and then this concentration, so it's in molar. I have 1, 2, 3, 4 decimal places in my pH, so that means I should have 4 sig figs in your concentration measurement, right? So make sure you understand the rules for how we carry sig figs when we calculate pHs. So it'd be 1.122 times 10 to the negative 12 molar. And lastly, concentration of hydronium ions is equal to 10 to the negative 8.01. Punch that into my calculator. I get 9.7724. Oops. 7724 times 10 to the negative 9 molar. I have 2 decimal places, so I would need to round to 2 sig figs. So this would be 9.8 times 10 to the negative 9 molar. That would be my concentration of hydronium ions in a sample with a pH of 8.01. All right, so now we're going to do the same thing for hydroxide ion concentrations. It's the same sort of game where pH, POH is equal to the negative log of concentration of OH. Here I know my hydroxide concentration is 3.7 times 10 to the negative 5, so my POH is going to equal the negative log of 3.7 times 10 to the negative 5. Punch that into my calculator and I get 4.43179. And again, my rules for sig figs are however many sig figs I have in my concentration, I should have that many decimal places in my POH. So 4.43 is my POH. Likewise, in this example, we have the negative log of 4.100 times 10 to the negative 7. Punch that into my calculator, and I get 6.38721. I need even more than that. 1614. Right here, I have 4 sig figs. So that means I'm going to need 4 decimal places in my POH. So this would be a POH equal to 6.3872. All right, and I'll leave you guys to do this one on your own here. It's pretty straightforward. I think that once you get the hang of finding that log button, making sure you know how to take the negative log or -1 times the log, it's pretty straightforward. All right, lastly, we're going to calculate the hydroxide ion concentration given a POH. So hydroxide ion concentration is equal to 10 to the negative POH. So for A, we would take 10 to the negative 4.91. Okay. punch that into our calculator, and we would get 1.2303. Times 10 to the negative 5. And again, the only kind of tricky thing here is the sig figs. I have 2 decimal places, 1, 2 decimal places. So I'm going to round to 2 sig figs for my concentration. And again, concentration always in molar. So this would be 1.2 times 10 to the negative 5 molar. All right, so these other examples are worked out in the lecture slides. I'm going to leave them to you because they're pretty easy. I actually want to do one other kind of calculation though. And this asked for the hydroxide ion concentration given the POH. What if instead it had asked for the hydronium ion concentration? So there's 2 ways that you could do this. One is to first solve for the hydroxide ion concentration. That's what I have here. And then use this expression that hydronium ion concentration is equal to 10 to the negative 14 divided by that hydroxide ion concentration. So I could just plug that in there. The other thing that I can do, and this is what I wanted to do with this example, is utilize this third equation that we saw here, the relationship between the pH and the POH. The fact that pH plus POH is always equal to 14. So basically for this, let's do it actually with this next example here. Example B. B, I have the POH equals 9.030, right? Well, if I took the fact that pH plus POH equals 14, I could subtract pH from both sides. So 14, oh, whoops, that's not what I want to do. I want to subtract the POH from either side. And I would see that right, so now I'm going to subtract POH. That will cancel that out on this side. So I would get that the pH is equal to 14 minus the POH. So pH equals 14 minus POH. My pH then would be equal to 4.970. And then I can plug this in. My concentration of hydronium ions is equal to 10 to the negative pH equal to 10 to the negative 4.970. Punch that into my calculator and I get 1.07152 times 10 to the negative 5 molar. I have 3 I have 3 decimal places on my pH, so that means I should have 3 sig figs in my concentration. So this would have a concentration of hydronium ions equal to 1.7 times 10 to the negative 5 molar. Right, and you would get that answer either way in which you approach that problem, either by first calculating the pH and then plugging that in to get the hydronium ion concentration, or if you first found the hydroxide ion concentration and then use this equation. Either one of those would get you to the same answer. I wanted to do a problem that utilized this pH plus POH equals 14 formula.